Let's first look at a really interesting model from NVIDIA called PixelDiT. Sounds powerful, right? But when we look at the images it generates, the texture, the naturalness of the details, and the overall quality are not especially impressive. There are even some obvious problems. So a lot of people may ask, why are we talking about a model whose results are not that good? Actually, the main focus today is not this model itself. What we really want to talk about is another model in the same technical direction, called PiD. The most attractive thing about PiD is that it can upscale images to 4K while also having very strong image restoration ability. Let's look directly at the results from PiD first. These images are close to 4K level. You'll notice that it is not simply stretching the image larger. The character's skin, hair, clothing, texture, and background lighting all get a lot of details reconstructed. This kind of result no longer feels like traditional sharpening. It feels more like the model has re-understood the image and then regenerated it again at a higher resolution. There are already many tools that can do 4K upscaling today. The part that makes PiD truly worth studying is its very strong restoration ability. With a normal upscaling model, if the original image is blurry, it will usually still be blurry after upscaling. It does not really have restoration ability. But PiD is different. During the upscaling process, it can reconstruct unclear faces, textures, and other details from the original image. Next, let's go through some basic theory so you can understand more clearly what these two models are actually doing. First, you need to know that both PixelDiT and PiD are related to one term, pixel space. When we talk about generation models, we usually have two spaces. One is called pixel space, and the other is called latent space. In most workflows, we operate in latent space. The model first generates in latent space, and then uses a VAE to decode that latent into an image. The benefit is that it is fast and low cost. The problem is that the VAE decoding step may lose details, especially textures, text edges, and small objects. These can easily become compressed and not clean enough. PixelDiT takes a more aggressive approach. It is a DiT diffusion model that generates images directly in pixel space. Its goal is to bypass the loss caused by latent compression and let the model directly process pixel-level details. Since the image quality generated by this model is not very high at the moment, its real significance is that it explores a possible direction. So the model we'll focus on is the one below PiD. PiD also works in pixel space. So what is the full name of PiD? It stands for Pixel Diffusion Decoder. That means it is not a text-to-image model. It is a latent decoding and upscaling model. It directly uses pixel diffusion to turn latent data into a high-resolution image. You can understand it like this. PixelDiT is a text-to-image model in pixel space, while PiD is a decoding and upscaling model in pixel space. PixelDiT tells us that pixel space diffusion is a direction that can work. PiD applies that direction to something more practical, high-resolution decoding, 4K upscaling, detail reconstruction, and image restoration. ComfyUI officially supports this model now. You can go to the ComfyOrg repository on Hugging Face. On that page, the file locations are explained very clearly. If you want to use the PixelDiT text-to-image model, you need to download that file. You also need to download a text encoder. If you want to run a PiD workflow, there will be more model files. Because PiD has different versions depending on the base model and the target size. For example, for Flux 1, there is a 512 to 2048 version and a 1024 to 4096 version. Flux 2 and SD3 also have corresponding versions. There is one important point to note. PiD is not currently a universal image upscaler. This set of models from ComfyOrg is mainly used with SD3 and Flux latents. Now let's briefly break down the workflow. For easier demonstration, I also built the workflow on RunningHub. In the ComfyUI space, RunningHub is a really great online workflow platform because whenever new models or new extensions appear, it usually follows up very quickly. RunningHub also provides an online community platform for ComfyUI creators, where you can find a lot of creative inspiration and example workflows. Let's first look at the PixelDiT text-to-image workflow. Here, the model we load is a BF16 model. The text encoder is a Gemma 2 encoder, and the clip type must be set to PixelDiT. For the positive prompt and negative prompt, you can write whatever you want. For the VAE loader, we choose pixel space. Pay attention here. In order to keep the overall workflow structure visually consistent, ComfyUI still keeps the concept of latent here. But you can remember one simple sentence: PixelDiT does not rely on a traditional VAE to generate images. For sampling, just follow the official setup. Finally, we decode it and get an image. Of course, this part is mainly for you to understand the idea. Now let's look at the basic PiD workflow. This is not a text-to-image workflow. It is an upscaling workflow. So first we start with a reference image and then we encode it. During encoding, we do use a VAE, but pay attention right now, the supported formats are only Flux and SD3. Here, I'm using Flux 1. When choosing the PiD model, you need to choose based on your upscaling goal. Here, I'm using the Flux 1 model that upscales from 1024 to 4096, and it is a 4-step upscaling model. The encoder is unchanged, it is still Gemma 2. The clip type still needs to be set to PixelDiT. For the prompt, I wrote something very simple, best quality. Here, there will be 2 VAEs. The first one is the Flux 1 VAE, which is used to encode the image into latent space. Then we run sampling. After sampling, when we decode the result, we no longer use that VAE. Instead, we use what we call pixel space. Now let's look at the sampling. The sampling process in this PiD workflow is quite short because it only uses 4 steps. The sampling algorithm is LCM and CFG is 1, so you'll notice that the speed is very fast. But because it uses LCM sampling, some images may carry that common LCM style texture. For example, the skin may look a little plastic, and some details may look overly clean or almost like they were redrawn. So PiD is not a mindless replacement for every upscaling model. It does have real restoration ability, but it also has its own style and limitations. In this workflow, there are 2 very important nodes. The first one is called context window. The second one is called PiD conditioning. Let's start with context window. This node is designed for high-resolution image generation. A 4K image is already very large. The model cannot easily process the entire image at once, the same way it processes a 1024 image. So it splits the large image into windows and processes them in parts. This is what we call the context window. Since my target resolution is 4096, I set the context size to 2048 and the overlap to 512. The fuse method is pyramid. What kind of mode is this? You can simply understand it as splitting the large image into blocks first, and then combining those blocks back together. We use this mechanism in many places. For example, when we talk about tiling, the underlying idea is basically the same thing. The second node is called PiD conditioning. This node understands how to process the input latent. There are 2 key points here. The first is latent format, meaning which VAE generated this latent. You can choose Flux or SD3. The second key point is degrade sigma. This parameter controls how much the input latent is degraded. That sounds a bit abstract, so let me say it more directly. The smaller degrade sigma is the more conservative PD becomes. It is more like upscaling while respecting the original image, with only light detail repair. The larger degrade sigma is the more aggressively it repairs and reconstructs the image. But at the same time, consistency with the original image may also decrease. So essentially, this parameter is controlling a trade-off. Now let's demonstrate it. First, look at this image. The original image itself is not very clear, especially the character's face. After upscaling, the details are not stable enough. If we use a normal upscaling model, it will most likely enlarge the blurry areas along with everything else. So first, let's set degrade as sigma to 0.1. This is the value used in the official workflow. Now let's look at the result. The image has indeed been upscaled to 4096, but the face is still not clear enough. It feels more like the original image was enlarged, rather than truly restored. So 0.1 does not work well here. Now let's go directly to 0.5 and sample it again. You can see that the change is much more obvious. Now the character's face becomes much clearer. The eyes, the edges of the facial features, and the skin details are all reconstructed. This is the very interesting part of PiD. It does not only do super resolution, it regenerates usable details at a high resolution. But when the restoration strength goes up, the model starts guessing information that did not exist clearly in the original image. If it guesses correctly, that is restoration. If it guesses wrong, it changes the identity, changes the facial features, or changes the texture. So for many portrait restoration cases, 0.5 is a practical starting point. Next, let's look at a more extreme example. This image is basically almost unusable. The noise is very heavy, the details are very broken, and the facial information is very poor. First, let's set degrade as sigma to 0.5. You'll notice that PiD can indeed restore the overall image. The scene becomes clearer and the character outline becomes more stable. But pay attention, the details are still not ideal, especially the character's face and eyes. So in this situation, you can consider increasing the restoration strength further. For example, I set it to 0.75. Now sample it again, and you'll see that the facial details become much more natural. The image also looks more like a complete high-quality picture. So the correct way to use PiD is not to push every image to a high value like 0.75. Instead, you should first judge what the original image looks like, decide how much restoration you want, and then adjust this parameter. Finally, let's talk about usage suggestions. If you just want to quickly upscale a clear image, PiD may not always be the best solution. Traditional super resolution, Ultimate SD Upscale, SeedVR, or other upscaling tools may be more stable. PiD's advantage is not that it is the most stable. Its advantage is that it can both upscale and restore. If the original image quality is poor, PiD becomes more valuable than a normal upscaling model, especially when the face, clothing, texture, or background details are missing. In those cases, you can increase the restoration parameter. But I still recommend not pushing it very high right from the beginning. Another point is the LCM sampling algorithm we mentioned. When generating some details, LCM itself can have certain weaknesses. For example, it may lean toward a plastic texture, and some details may be polished too smoothly. You also need to keep this in mind during sampling. To summarize, PixelDiT itself is a pixel space text-to-image model with strong research value. But if we directly use it to generate images, the results are not especially good. So its greater value is that it points to a possible direction. In practice, we are more likely to use the PiD model. For normal ComfyUI users, you only need to remember 3 things. First, PiD can do 4K upscaling. Second, PiD can do more than 4K upscaling. It can also do restoration. Third, the way we control the restoration strength is through degrade sigma. This is the core parameter. The smaller the value, the more conservative it is. The larger the value, the stronger the restoration becomes. But consistency is also more likely to be damaged. All right, that's all for today. So what are you waiting for? Go try it yourself. Follow me and become someone who truly understands AI.